Hi everyone. So today we are going to talk about the work kinetic energy theorem. So we'll start with a problem here. This is sending a probe to Mars. We're going to start here to show how work can affect velocity, right? So we've got a probe with food for Mark Watney from the movie The Martian. The probe has a force of attraction with the sun shown as f of x equals negative 1.3 times 10 to the 22nd x to the negative 2 power, where f and x are in SI units, and x is the distance between the probe and the sun. So first, let's sketch a graph of f of x and show the work graphically on the sketch. Well, what we'll do here. So the 0, 0 is up here. This is the origin. Okay. Here is, this is f versus x. So this is x in meters. And this is force in newtons. So if you graph this equation, it looks something like this. And the work done here, right, is going to be the shaded area under the curve. In this case, it would be above the curve, right? So it would show that it's negative work, that it's working against the object as it gets farther and farther from the sun. So what we want to do is we want to use calculus to find the work done by the sun on the probe as the probe goes from Earth to Mars. And we have the distances there. The distance from the sun to Earth is 1.5 times 10 to the 11 meters. And the distance from the sun to Mars is 2.3 times 10 to the 22nd meters. So to do this problem, what we will do is we want the work. So that would be the integral from the Earth to Mars of our f of x dx, right? So that would be the integral from, what is it, 1.5 times 10 to the 11 to 2.3 times 10 to the 22nd. And our equation is negative 1.3 times 10 to the 22nd times x to the negative 2 dx. Now that x to the negative 2 is like being divided by x squared. So if we take the integral of this, we would get negative 1.3 times 10 to the 22nd x to the negative 1 divided by negative 1, so that negative 1 and this negative cancel. So what we end up with is 1.3 times 10 to the 22nd divided by x from whatever xe to xm are. So now we do final minus initial to get our value, because this is a definite integral. So we would take 1.3 times 10 to the 22nd divided by 2.3 times 10 to the 22nd minus 1.3 times 10 to the 22nd divided by 1.5 times 10 to the 11th. So we took the distance from the sun to Mars, that's our final. The distance from the sun to Earth, that's our initial. And when you put that in a calculator, it all comes out to negative 8.67 times 10 to the 10 Newton meters. That is how much work is being done against the probe as it goes from Earth to Mars. Now, the real question we want to look at here is how would this affect the speed of the probe? So if something is working against you, right, it's going to start slowing you down. And that phrase of work is going to work, it's going to be accurate here as well. That is going to start pulling the velocity vector towards the sun, and it's also going to slow the speed of the probe by both changing the magnitude of the speed and changing the direction. So that's how work can actually affect velocity. Now let's look at the next slide to talk more about velocity. Okay, let's talk about kinetic energy, and these will compare, or these will meet up in the middle in a second. So we have this data. These are the kinetic energies for various objects. We've got the kinetic energy of Earth orbiting the sun, Moon orbiting the Earth, a rocket moving at what is called escape speed or escape velocity, an automobile at 65 miles per hour, a running athlete, a stone dropped from 10 meters, golf ball at terminal speed, raindrop at terminal speed, and an oxygen molecule in air. So we have these various, it has the mass of the object here, then we've got the speed of the object here, but then we have the kinetic energy of the object here. So what we want to do is we want to use this data to rediscover the equation for kinetic energy. If you already know the equation for kinetic energy, this will be pretty easy for you. But if not, it's kind of complicated to figure out how to make these all match. So what I'm going to do is I'm going to use the stone dropped from 10 meters. This, since the mass is 1, it's very easy to do. So if you want to take mass times velocity, that gives you 14. Well, that didn't do anything for us, right? If we want to get this really big, really fast, we can just do mv squared, right? Mv squared is going to give you 196. That's bigger than 98. It's actually double of 98. So if we take that down to 1/2 mv squared, you would get 98. So this is our equation for kinetic energy. Many different, that was just a fun way of looking at all these kinetic energies and finding out a way to get kinetic energy from that. Now, if you want to try it with those other quantities, be my guest. We usually do that a little bit in class. Like someone will try the running athlete or the car or the golf ball at terminal speed. All of those are great options. But the equation for kinetic energy, 1/2 mv squared, and that's instantaneous velocity, right? If there's a change in velocity, then we've got to look at that in a different way, which we'll talk about here. So work can change the speed of an object. We talked about that. Now, there is something called the work kinetic energy theorem that actually shows a relationship between work and kinetic energy. So let's go through this. I'll do the mathematical statement on the left and then the reasoning on the right. So first, we will start with the definition of work, which is the integral from x naught to x final of a force function with respect to x. Okay, that is just the definition of work. Now, we now need to start modifying this equation. So what we can do is we can say F equals ma. Let's make that substitution. So if we go from x naught to x final of ma dx, that's a start, right? Now there is no x in that equation to begin with. So let's start breaking these things down. Acceleration is the derivative of velocity with respect to time. So if we take the integral from x naught to x final of mass times dv over dt times dx. Now, that doesn't mean a whole lot to us, but all of these can move around, right? You've got m times dv times 1 over dt times dx. Well, if the dv and 1 over dt are combined, that has meaning. We could also combine these two. If the dx is multiplied by that, that also has meaning. So let's give that a shot. We have the integral from x naught to x final of m dx over dt times dv. Now there are so many d's in there that gets kind of complicated, but what is dx dt? Okay, so dx dt is velocity. So now we also have a dv in there. We need to change our bounds. That would be from v naught to v final of mv dv. Now if we're going to, now we can just evaluate the integral. The integral of mv would be mv squared over 2, right? So you have mv squared over 2 from v naught to v final, which comes out to 1/2 m times v final squared minus v naught squared. And this equation right here, that is actually delta K. That is the change in kinetic energy. So the work kinetic energy theorem can show that if there is a change in kinetic energy, it took work to do that, and we can calculate that work. So work is actually equal to the change in kinetic energy of an object. So this is big. Now we can look at not only forces with work, we can now look at velocity regarding work. So let's look at this. We've got an example problem. Calculate the work done to change a specific velocity. Right? So we've got a 3 kilogram mass, has an initial velocity of 6i minus 2j. We will calculate the initial kinetic energy, then calculate the total work done on the object if its velocity changes to 8i plus 4j meters per second. So we want the initial kinetic energy. So initial kinetic energy, K naught would equal 1/2 mv naught squared. We don't have v naught, so let's find v naught. V naught would be, well, we have the component form. Let's just get the magnitude of that. So that would be 6 squared plus 2 squared. We'll just do the Pythagorean theorem. That will give us square root of 40, 36.4, yeah. Square root of 40 meters per second. So if we plug that in up here, we've got 1/2, 3 kilograms for the mass. Square root of 40 squared is just going to be 40, right? So you've got 3 times 40 is 120, divided by 2 is 60 joules. And remember, kinetic energy is joules. Work, we've been using Newton meters, but those are interchangeable. Now, that's the initial kinetic energy. Now let's calculate the total work done on the object if the velocity changes to 8i plus 4j. So if we have a v final of 8i plus 4j, let's do 8 squared plus 4 squared. A Pythagorean theorem, that's 64 and 16. That gives you 80. So you've got square root of 80 meters per second. So if we want to know the work, we want to know the delta K, which would be 1/2 m v final squared minus v naught squared. We have v naught squared, right? Or we have v naught, v naught is square root 40. And v final is square root 80. You could also do k final minus k naught, right? That's also how you can find change. So we'll do them both ways, right? You can do 1/2 times 3 times v final squared. So square root of 80 squared is 80 minus square root of 40 squared would be 40. So that would be, that's again 60 joules, right? Now let's see if that equals k final minus k naught. K final would be 1/2 times 3 times square root of 80 squared. We already know K initial. K initial is also 60. Okay? So we break this down. 80 divided by 2 is 40. 40 times 3 is 120. So you have 120 minus 60. That also gives you 60 joules. So both ways you can get the job done. Right? So that's how we can use the work kinetic energy theorem to go back and forth between kinetic energy and work. So that's the work kinetic energy theorem. We will continue on through chapter 7 in our next video.